Well, welcome back to videos. It's been a little while since we've had a new one, but today we're starting off the first video of Unit 2. We're through that introductory stuff that has a lot to do with kind of getting us started in how we're going to do things in chemistry in terms of measurements, in terms of calculations, scientific method, did a little bit on experimental design, and sort of all the introductory topics that hopefully we've got those out of the way now, and we can get on to the real meat and potatoes of the class, which starts off with atomic theory. So our first look is going to be at a little bit about how atoms came to be understood the way that they are today, some of the different people that have helped us get there, and some of the advances that were made through hundreds and even thousands of years in terms of get us to where we are today in the 21st century and what we now have for understanding about atomic theory. Our first sort of character then will be today's introductory guy, and his name is Democritus. So we'll take a look at him first. Democritus came to us in the almost prehistoric times of science, if you will, 400 BC. Democritus's contributions in 400 BC are some of the first that we have. He's certainly not the first to contribute anything to the atomic theory, but he gives us our first sort of important contribution, and so he's the first name that I'll put down in your notes with you. His story kind of starts out with what I imagine would have been a walk on the beach. Democritus walking along the beach one day sees the sand that stretches out into the horizon in front of him as a continuous ribbon of sand, and he picks up a handful of sand and lets it fall through his fingers and imagines that since the sandy beach that looks like it's continuous and goes on into the horizon forever, if you look up close, is made of tiny pieces, he wonders if maybe those tiny pieces aren't made up of smaller bits still. And if he took a piece of sand and cut it in half, and then cut that in half, and cut that in half, if he couldn't eventually come to the point where he got to a piece that was so small that it couldn't be cut, and he believed that that was true. He believed that all matter was made up of tiny indivisible particles, something so small that it couldn't be cut. At the very most base unit of all matter, including those sand grains or the water in the ocean that was near him. And so he believed that matter had a smallest unit, a smallest particle. We say that Democritus and others believe that matter is particulate. And there's an opposite to that you'll be getting to here in just a second. So he gives us the word, which comes from simply the Greek word for uncuttable, which means what he believed matter to be, some smallest piece that wasn't cuttable. And he called that then the particle atomos, which means uncuttable. And so if you can see there in that 6-letter Greek word is our 4-letter English word, the atom, and one that is kind of stood the test of time ever since. At the same time as Democritus was another character who you've probably heard of and is a lot more familiar with, Aristotle. So around the same time frame was Aristotle. Now you have to remember, as we talk about these early guys, they weren't publishing books, they weren't going to conventions or conferences like scientists of today would. They were simply teaching their students what they believed and being very convincing about it. So if you wanted your idea to be passed on, you had to be convincing. You had to teach a lot of people your idea and hope that they bought into it and would pass it on to theirs and on to their students and on to their students, and they would get through time that way, sort of more of an oral tradition. Certainly making notes on scrolls and this sort of thing, but not being published and widely disseminated out to the world, and so you had to just be convincing. Aristotle had a very different perspective on what matter would be about. Aristotle believed that matter was continuous. He believed in the 4 elements that were known at the time: earth, wind, water, and fire. Sometimes you'll hear it called earth, air, water, and fire. Matter wasn't, in the mind of Aristotle, matter wasn't made of small bits. It was continuous sort of stuff. He actually had a word that would sort of be the counter to the atom, and that word was hyle, which I believe is spelled Hyle. And that word sort of is the stuff of which matter was made, according to Aristotle and his beliefs. That's what he would tell his students matter was made of. Not little pieces that you could cut it up into, but it's just stuff. You're bigger than the person next to you or smaller than the person next to you because you have more or less stuff in you than that more or less of this 4 basic element combination. Well, the trick is that back then there wasn't really science so much as there was philosophy. There wasn't science at all for quite a while afterwards, and we'll talk about sort of the first contributor to that here in a bit. But neither one of them could go ahead and prove their hypothesis to others in a scientific way, and so based on being convincing, they would pass their idea on. Trick is that Aristotle at the time, and he's probably would we find out with you in the present day, his name's a lot better known. He was a lot better known on other things too. And frankly, Aristotle was dead wrong on this, but he'd been right on a lot of things. And so his ideas were passed on and accepted, and he became sort of the standard in what we would now call atomic theory, even though he didn't believe in atoms really at all. So his ideas were held, followed, and Democritus' ideas of the 400 BC, the 4th century BC, were long forgotten for many, many years. So this is all prior to what we would call science as we see it today. Before science, before the scientific method, back then, you couldn't prove, you couldn't test a hypothesis because there wasn't such a thing. There wasn't observations, hypotheses, experiments, conclusions. There wasn't a scientific method. You just had to be convincing. And Aristotle was more convincing. I like to imagine that Democritus would be standing on a street corner explaining his idea. Come one, come all, listen to me. I believe matter is made of these small pieces, these small particles that can't be divided any smaller. And on the other street corner would be Aristotle promoting his ideas, saying, oh no, matter's not particulate, it's continuous, and that's just the opposite. And they go back and forth sort of debating their two sides, seeing who could be more convincing. And whoever was more convincing or maybe better looking, had better hair or nicer clothes, I don't know, would be the one who would be accepted. Not based on science, but on who was more convincing. Which to me is frighteningly similar to what we do with today's modern elections. It's not so much that you've got any proof of what you believe to be the solutions for our country will actually work. It's just that you sound a lot more convincing. Maybe you're more eloquent of a speaker, and so we vote for you instead of the other person. Perhaps you look a little bit more photogenic on TV. All very scary stuff. Bad ways to choose our elected officials, and 2,400 years ago, a really bad way to choose what we believe in science because it set us back for a long, long time. So, before science came around, there wasn't a great method of doing it until around the 1600s. And here's a fellow you see on the screen, Sir Francis Bacon, the father of experimental science in the 1600s. He was earning that name because he came up with the idea of testing a hypothesis instead of simply arguing about it. What do you know? Testing and proving your ideas as true rather than trying to simply argue as being more convincing or try to diffuse or refute the other person's argument. Sounds a lot better to me. And so with him begins the era of modern science and our understanding of how to prove ideas today. Anybody can have a great hypothesis, test it, prove it to be true, and pass it on to others. You don't have to be a great speaker. You don't have to be good looking like Aristotle might have been in order to get your ideas across. It's a lot better way, especially for us nerd looking fellas like myself. Sir Francis Bacon, then, we'll pass over. We won't give you a lot of details more about him than that, other than the fact that he turned us to the idea of science. And that's not just for chemistry, that's really for all science, because the idea of hypotheses and experimental design crosses over to physics, astronomy, biology, geology, all sides of science. The next character in our atomic theory is a guy by the name of John Dalton. So we've jumped ahead now to the early 1800s, a long time from Democritus in the 400s BC up to the 1800s of modern time. We're down now to the last 200 years or so. And really only now does chemistry get started in the last 200 years. We're a very young science when it gets right down to it compared to things like physics, certainly. We're very, very young. Physics is sort of the underlying foundation to all chemistry anyway. And so you'll start to find out that a lot of the key players in chemistry and atomic theory were physicists, not chemists, because there really weren't chemists yet then. John Dalton was a British school teacher, and he took, as many scientists do, he took the ideas from people who'd come before him and built them into something bigger or better or more understandable or maybe more correct. The two people we'll mention here are Joseph Proust and Antoine de Lavoisier. Both of them contributed a lot of things to our current modern atomic theory, and we'll talk more about their names as we go, especially Lavoisier comes back later on in chemistry. Dalton came up with eventually a 5-part atomic theory, at least the way I'll present it to you will be in 5 parts. It turns out that certain parts of Dalton's atomic theory we now know to be false. Some of them true, some of them false. Certain parts of some of them are false and true as well. And I'll mention those to you as we go. So Dalton's atomic theory comes in 5 parts. The first is fairly straightforward. His theory is based on the idea of Democritus, which was that matter consists of definite particles, individual pieces called atoms, and that those are indivisible. Those are the smallest possible pieces of matter. Turns out the very first part of Dalton's atomic theory is actually slightly false. We now know that atoms aren't indivisible. We can split the atom. That's nuclear fission and fusion that we talk about. In this case, nuclear fission. Atoms can be split, and tons of energy can come out of them when they are split. That's our whole idea behind nuclear power to some extent, and we'll talk more about some of those ideas as we go through the year. The second part of Dalton's atomic theory is that all atoms of a given element are identical in mass and other properties. In other words, all of the atoms of silver in the world are exactly the same, or all of the atoms of carbon in the world are exactly the same. Turns out that number 2 here on Dalton's atomic theory is also, in fact, very false. And we'll talk more about why later. You'll find out the word isotopes becomes very important. And isotopes are the simple reason behind why number 2 on Dalton's atomic theory list is also false. Now, there are certain things about atoms of carbon or silver or any other element that are the same. Every atom of carbon has certain things in common, and every atom of carbon has those exact same properties as well. But there are also parts of carbon atoms or silver or gold or any element out there that are different. And so not every gold atom is exactly the same as every other one in every way. Some ways it's the same, some ways it's not. Number 3 states that atoms of different elements are different in some essential way, and that compounds form when atoms of different elements are combined. Well, this is very true. Everything about number 3 is effectively true. There are things that atoms have in common even between other elements. Carbon and nitrogen, for example, we can take atoms of each of those and find similarities, but they are certainly different in some essential way. That's why they have different names. That essential way, their most basic identifier, will be the protons, and we'll be talking more about how we came about understanding protons later on. But number 3, definitely true, still believed to be very true. A couple more things about Dalton's atomic theory. Number 4 is that atoms cannot be destroyed. This kind of goes back to that second part where there were definitely some splitting possibilities, or rather the first part, of Dalton's atomic theory. It goes back to that first section where we say they aren't indivisible because we know they are destroyed. But the second part of this is critically important, and it's very true. In chemical reactions, the atoms rearrange, but they do not themselves break apart. So when we have a reaction between, as you saw in the first lab of the year, candle wax and oxygen, we have carbon, hydrogen, and oxygen atoms, and those 3 atoms are recombined into new things, carbon dioxide and water, but not themselves destroyed. So the atoms are still there, the same number of atoms are still there, they're just rearranged into something new. And that comes from Lavoisier, and something that we'll talk more about with him when we get to stoichiometry much later in the year. And finally, the last section of Dalton's atomic theory is that in a certain compound, like water, sugar, carbon dioxide, salt, in a certain compound, the elements are always found in the same ratio. That's very true, and this comes again from Proust's work on definite proportions, which means that water, H2O, will always be H2O, which means it's a 2-to-1 ratio. H2, 2 hydrogens, O, 1 oxygen. So it's always going to be a 2-to-1 ratio. Anytime you see hydrogen and oxygen in a 2-to-1 ratio, it'll always be water, and mutually inclusive, if you will, the other way, every water molecule will always be H2O1. So it's a very elite and specific way of putting those 2 elements together, which is important because there are other compounds that can be made from those same elements as we go that are very different things. That's it for this. We're going to end there with Dalton as our kind of conclusion for the night, and we'll be back with our next couple characters and actually start talking about some of the subatomic particles that are part of the atom too.